Good morning to all of you in Australia. Good evening or late afternoon to Funing Lee, who's our speaker today. Before we start, I'd like to acknowledge the lands of the traditional owner of the many lands we are meeting on today. I am on Wadawurrung land, which is the land of the surf near the surf coast where I am at the moment. And it's a great pleasure to have Funing talking to us. Funing did his PhD at Purdue, thinking about convection and tornadoes and all the severe stuff that goes with convection. He's most broadly interested in, as you would have seen on his little bio, on looking at extreme weather, but in the context of what's causing it and what the large scale and smaller scale processes might be. So he fits perfectly into the agenda of 21st century weather. And after his PhD, he went to MIT, who you may or may not know are an official formal partner of the center. And there he's looked at extreme heat and convection, and in particular, he looked at humid heat, which is also what he's going to talk about to us today, about his work he's done at MIT. And the title of his seminar you can see on the screen there. So with no further ado, I will hand over to Funing to give his presentation.
Okay. All right. Thank you so much for introducing me. And thank you for everyone coming to my talk and for having me present here. So yeah, today my talk will be focusing on my recent work during my postdoc to talk about the results on the physics and projections of moist weather extremes in the mid-latitude, especially over the land region. So I guess the significant damage caused by extreme weather is perhaps one of the main reasons we want to better understand these events so we can improve the prediction and also risk management of these events. So for example, this map is showing you the billion-dollar loss extreme events across the globe in 2025. What stands out is that most of these extreme events are focusing on the mid-latitude land regions. For example, in the United States, the Europe and also eastern part of Asia and some of the southern hemisphere land regions. So even though these extreme events spans a wide range of categories, but actually most of these events are dominated by either the severe convection or near surface heat condition. Near surface heat conditions. And in terms of the total loss of these events, you will be see the severe convective storm is the most damaging extreme events, followed by wildfires, which again are closely related to the extreme near surface heat condition. So even though those no risks of extreme events to the society and human, how extreme weather will evolve in a warming climate still remains quite uncertain. And a big source of this uncertainty is our limited understanding of the underlying physics controlling their evolution across scales. So for example, global climate model in general predicts higher convective available potential energy, or CAPE, which would suggest more severe convective storms in the future warmer climate. However, at the same time, the convective inhibition, which serves as a barrier to convection, is also projected to intensify in the future warmer climates. So then you can imagine this competing influence from these two parameters, make it really difficult to actually interpret how these convective storms will actually respond to the warming in the future climate. And it becomes even more complicated and challenging when we try to think about some regional variations of a specific type of severe convective storms. For example, this historical eastward shift of tornadoes based on the observations focusing on the central United States, which is based on the historical observations of tornadoes. But we really don't have a very clear understanding about why this shift is happening and to what extent this shifting will be continued in the future warmer climate. And for extreme heat, it may not be very surprising that the high temperature days are becoming more frequent in the future warmer climate. But the uncertainty comes in when we try to quantify the risk induced by heat to the human body, when the humidity also plays a critical role in addition to the temperature. So in general, a combination of high temperature and high humidity produce the more dangerous condition to human body, and which can be measured by Webb temperature. And then what you can see from the bottom of the slide is the global climate model also projects an intensification of Webb temperature in the future climate, but it shows more localized applications, especially some extension from the tropical region into the mid-latitude land regions. And another issue is that the moist heat has been relatively overlooked in the mid-latitudes as compared to the tropics. For example, this is showing you the National Weather Center in the United States, which has been used in the heat index to measure the moist heat stress to human body. But recent study, they show there has been a fundamental bias in the heat index, which could cause a very strong underestimate of the moist heat stress, especially in the United States. And after they corrected this heat index, they found that the Midwest United States, instead of the southern part of the United States, would have experienced some of the most severe moist heat events in the history, which has been largely overlooked in the past. So with this background, my project emphasizes on both the extreme moist heat and extreme deep convection. But before I start to talk about the results, I just want to make some definitions clear that is relevant to what I'm going to talk about. So I use 3-hourly EI fiber analysis data, which is closer to observations, and also 6-hourly outputs from the global climate models of CMIP6 to look at the projections of these events. And we focus on the most extreme moist heat and potential convection over the mid-latitude land region. So for moist heat, we look at the annual maximum condition of the moist heat events, which is defined by the annual maximum near-surface moisture static energy at each land grid point. So MSE is the sum of the near-surface sensible heat, latent heat, and geopotential energy, which has a functional relation with the Webb temperature that has been more commonly used by the community to measure the moist heat stress. But as you can see, the MSE is the formulation of MSE is similar. So then it will enable us to easily decompose the contributions from temperature and moisture to the variations or changes of the near surface moisture static energy or moist heat. And also examine the annual maximum potential convection, which is defined using the convective variable potential energy or CAPE. So CAPE is commonly used by the community to measure the potential intensity of convection because it gives a theoretical estimation of the maximum updraft velocity of convection if it is initiated. So one key reason we can study these two events or these two extreme moist events together is that the most extreme moist heat and the most extreme convection often occur at the same time, especially across the mid-latitude land region. So you can see this from a typical atmospheric profile during the annual maximum moist heat. So what I'm showing here is a representative sounding over the central United States when the near surface moisture static energy or moist heat is maximized during the year. So the dashed line here is representing the temperature profile of an air parcel lifting from the surface to the free troposphere, assuming a adiabatic process. And the solid line is representing the temperature profile of the environments. So then when you compare these two temperature profiles, it will give you the information of the buoyancy for this air parcel. So when the temperature of the parcel is warmer than the environmental temperature, means positive buoyancy, which tends to lift the air parcel. And if it's cooler than environmental temperature, then it's negative buoyancy, which will suppress the onset of convection. So what you can see from this typical sounding, it is characterized by a very deep layer of positive buoyancy. So it's corresponding to high values of convective variable potential energy or CAPE. And at the same time, if you look at focusing on this low-level atmosphere, there are some, it's overall very stable. You can see some very slight negative buoyancy, but it's pretty small, very close to zero. So which means the convective inhibition or sin is also close to zero for this typical sounding associated with moist heat condition. So this combination of high CAPE, low sin is also favorable for the onset of deep convection, which has been commonly thought to help terminate the heat wave evolution. This co-occurrence of moist heat and convection extremes is actually pretty general to the land regions over the mid-latitudes. So over the past 40 years from the EI fiber analysis data, what I'm showing you here on the top, this is just the annual mean, annual maximum moist heat, and the annual mean, sorry, the mean annual maximum moist heat over the past 40 years, and the mean annual maximum CAPE over the past 40 years from the EI fiber analysis data. But then we can also just compare, like, to what extent these annual maximum events of this, at the annual maximum values of these two events overlap with each other. So this is what you can see from this, this map. So you can see over the past 40 years, more than 50% for most regions, the annual maximum moist heat and the annual maximum potential convection, they occur exactly at the same time of the year. So even for some cases, they don't occur at exactly the same time. We do see the annual maximum moist heat is usually followed by relative extreme condition of potential convection. So this can be seen from the mean CAPE at the annual maximum moist heat on the bottom right. So you can see this mean CAPE at the annual maximum moist heat, which we call it as critical CAPE, is pretty close to the actual annual maximum CAPE on the bottom. So which again serves as the evidence to show this strong co-occurrence of the moist heat and moist convection across these mid-latitude land regions. But for simplicity, I will focus on the timing or cases of annual maximum near-surface MSE over the mid-latitude land region, and then use those cases to study how the near-surface MSE and the CAPE builds us towards their peak values throughout this time series. I just want to show that we also did a duration of a scaling CAPE just to build up a linear relation, theoretical relation between CAPE or potential convection and the near surface MSE or moist heat. So you can see the CAPE and near surface MSE is related by a very strong linear relation. So this is derived based on the definition of buoyancy and also CAPE, including this coefficient in front of this in front of the near surface MSE. So you can see from this very strong linear relation, you can also imagine the it gives a theoretical understanding about why the near surface MSE will reach the maximum together with the potential convection or CAPE. Of course, we need to assume this 500 MSE star will remain relatively unchanged. So this is representing the free troposphere saturated MSE, which is roughly at the height of 500 millibar. So this parameter is relatively unchanged, especially within a relatively short time scale. So, okay, so we talk about this co-occurrence of moist heat extreme and potential convection from the historical data. I just want to say this co-occurrence from the historical data is also reflected in their future applications on the warming scenario. So on the bottom is showing you the projected changes under the high emission scenario, SSP 585, using, I think it's using 4 well-performing models from the SMIP 6 to look at the projected changes of the annual maximum moist heat and the associated critical CAPE across the mid-latitude land region. So you can see they both have a very strong amplification in the warming scenario, and the pattern look pretty similar. So what's interesting and also very alarming is that these moist weather events has been historically stronger over the tropical regions because the tropical ocean are relatively warm and moist to support these moist extreme weather events, right? But in the future warmer climate, we see certain mid-latitude land regions, especially the northeastern Asia and the eastern part of the North America, extending from the Midwest to the northeastern North America. These two regions are potentially become the new hotspots in the future warmer climate for the moist heat and potential convection extremes. So then my task, and also for the rest of this talk, I'm trying to understand these maps I'm showing you here from the historical and also from the future projection to answer 2 questions. So the first one is, we talk about this co-occurrence of these 2 extreme moist weather events, but then what limits the moist heat and the convection maximum intensities across the mid-latitude land regions? And then the second question, which is based on the answering to the first question, we will try to understand the future application of these 2 extreme moisture events, especially to understand why these certain regions in the mid-latitude land regions emerging as the future hotspots in a warmer climate. So these works, I performed this work with my advisor at MIT East, Professor Tadia Tamarin-Brodsky, and we have these papers out recently. The one is already published early of this year, and the other one also have the preprint out on the website. Okay, so we talk about the physical limits on the surface moist heat and convection. I would say this problem is not it's actually very has been intensely studied, especially over the tropical regions. So it's also relatively well understood across the tropical ocean. As we said, some simple assumptions can be used to help us understand this problem, especially the coupling between the surface MSE and the free troposphere. So for the tropical ocean, the atmosphere is strongly coupled to the warm, moist ocean. And in that regime, convection is often treated as in quasi-equilibrium state, meaning that the synoptic variation in convective instability is relatively small. And then under this assumption, CAPE is usually assumed to be compensated by processes like entrainment. And then the near surface MSE or temperature can be tightly correlated to the free troposphere temperature based on the assumption of moisture neutrality of the atmosphere. And also we can further understand the land-ocean warming contrast by combining with some other common assumptions, for example, the wake temperature gradient assumption for the free troposphere. But this situation is quite different over the mid-latitude land region, where the severe convection is often associated with very strong buildup of convective instability across a relatively short time scale. And then for this regime, the convection can evolve, or the temperature profile of the column can evolve beyond the quasi-equilibrium state. And then this assumption we're talking about for the tropical region, for example, the moisture neutrality assumption does not hold for the mid-latitude land region. And this can be also evaluated using, for example, comparing the near surface MSE and the free troposphere saturated MSE, as what I'm showing on the bottom. So this is just for especially for extreme heat conditions. So this one is showing you for the cases of annual maximum moist heat conditions across the mid-latitude land region. So we can see here is for most of these cases, the near surface MSE is exceeding the value of the saturated MSE of the free troposphere, which means the departure of the atmospheric column beyond the quasi-equilibrium condition or the moisture neutrality condition. And it also pretty similar. This condition is also shown for the extreme dry heat conditions, even though for the extreme dry heat events, these moisture neutrality assumption might be more it works relatively better as compared to the extreme moist heat condition. But definitely for the extreme moist heat conditions, we need to consider this build up of convective instability across these time scales. I just want to elaborate further on this stored energy nature of mid-latitude convection. So let's just go back to this sounding what I showed in the earlier slides at the time when both the surface moist heat and convection are maximized. But now, if we look at the days, several days prior to this annual maximum moist heat condition, what do you see here? The sounding, they look different, right? But for the 7 days prior to the annual maximum moist heat condition, the sounding is already associated with some small convective instability, which is characterized by the small values of CAPE. But the convection did not initiate. The main issue is, or the main reason is, if you look at the low level atmosphere, the temperature profile is characterized by the very clear inversion layer. By saying inversion, it means usually the temperature will decrease with height from the surface to the troposphere. But for this sounding, you can see the temperature does decrease with height, but then there is a very shallow layer. The temperature starts to increase quickly with height. This produces a very strong temperature inversion. And this inversion also produces a lot of negative buoyancy, which can suppress the onset of convection. And then over time, what you can see, the evolution of the temperature profile, the free troposphere temperature profile, they do not change too much. What you can see here is a very strong buildup or increase of near surface temperature and also increase in the near surface moisture, which I didn't show here. But together, this near surface moisturing and warming are trying to overcome this very strong inversion structure within the lower atmosphere. And when the inversion is removed, you can see the scene is approaching to zero, and also CAPE is maximized, which will initiate the convection to terminate heat wave. So from this sounding, it also gives us some hint about the potential maximum intensity of moist heat and convection, which might be related to the pre-existing inversion I showed in the previous slides. Because this pre-existing strong inversion will create the most negative buoyancy that an air parcel must overcome to initiate convection and then terminate heat wave. So then the task is to quantify this process, right? So what I did is instead of writing the temperature as a function of the temperature difference between the air parcel and the environment, I just want to relate the buoyancy profile to the static energy, because that will enable us to relate this convection initiation problem or process to the near surface moisture static energy. So in the end, I'm not showing the details of the duration, but you can find that in my paper. But in the end, the buoyancy profile of the parcel can be written as a function of the static energy, but depends on the height of lifting condensation level. So if the height is below the LCL, then the buoyancy is proportional to the difference between the air parcel's dry static energy and the environmental dry static energy. If it's above the LCL, then it will be the difference between the near surface MSE and the saturated MSE over the environment. And it's good, as I said, because it builds a direct relation between the parcel's buoyancy and the near surface MSE, which is related to the near surface moist heat. And again, another very nice thing to use this framework is what I showed in the previous slides about the temperature inversion. This can be amplified in the static energy profile. So this is showing you the same profile of the sounding 7 days prior of the annual maximum moist heat, but using the static energy profile. So again, the difference between the dashed line and the solid line still give you the information of the buoyancy. But you can see under the static energy profile, you can see very clear this very strong thermal inversion, which is defined by this maximum saturated MSE above the LCL, but within the lower atmosphere. So then we can think about this onset of free convection. So clearly, ideally, we would expect the scene is approaching zero and CAPE is greater than zero, because this will enable the convection or free convection to initiate without any barrier in the low atmosphere, but strong buoyancy throughout this deep layer of the atmosphere. But from this sounding, as I said, it is equivalent to the minimum buoyancy approaching zero, because you can imagine if you move this dashed line from the left, from this profile, from this point to the right-hand side, to remove this negative buoyancy, then we don't need to worry about any scene, and also ensures a lot of CAPE for this sounding. And I just want to show the actual evolution of this sounding under the static energy profile. So you can see at the time of the annual maximum moist heat for this case, you do see the surface MSE or this dashed line is increasing strongly and to approach this very strong pre-existing inversion, even though there are some evolution of this inversion with time. But you do see the increase of the inversion is much smaller than the intensification of the near surface MSE. And again, this increase of the near surface MSE also substantially increase this convective instability or CAPE. So in the end, I just want to give you what we derived based on sort of this inversion constraint framework. So in the end, we just want to show it looks like the pre-existing inversion strengths could help us to determine the attainable maximum intensity of both moist heat and convection. So the near surface MSE here is defined by or constrained by the maximum saturated MSE or the strength of inversion within the lower atmosphere. And again, using the scaling framework of CAPE, we can also derive a potential maximum intensity of convective available potential energy over the atmosphere. So this also means the CAPE is also constrained by a function related to the intensity of the inversion, the MSE star max of within the low atmosphere. And from what we see, when we compare this potential intensity of near surface MSE or the potential intensity of CAPE versus the actual maximum intensity of near surface MSE or cape from the reanalysis data, we do see these actual maximum values are strongly or tightly close to the 101 line, but you do see most of these cases are below this 101 line, which does make sense because when we derive this relation, we expect the inversion or the thing are completely removed by the near surface heating or moisturing. But in reality, you can imagine the convection can initiate earlier if there's some external lifting forcing exists to help initiate the convection without completely removing CIM or negative buoyancy. I just want to show this is a composite time series to give a sense about how the time series of these key parameters evolving throughout the lifetime of the build-up of the maximum moist heat and convection. So on the left-hand side, so this is based on the composite time series, for the concurrent moist heat and convection cases across the mid-latitude land regions. So you can see the near surface MSE increase quickly with time towards the peak value, right? And then this increase of the near surface MSE is strongly bounded by the preexisting inversion. And at the time of the annual maximum near surface MSE, it is approaching this inversion strength, right? Or the MSE star max. And you can see the near surface MSE is already greater than this MSE star 500 or the photosphere saturated MSE several days prior to the annual maximum condition. And this exceedance of the near surface MSE from the saturated MSE at 500 is also reflecting the strong buildup of cape with time. So you can see on this one, the cape is also increasing with time quickly throughout this time series. But again, it's also bounded or predicted by this potential cape, which is based on the equation based on the pre-existing inversion strengths I showed in the previous slides. And again, as I said, the reason we can use the inversion to predict the annual maximum or the potential maximum intensity of cape and the inverse of cape and the near surface moisture static energy, because the pre-existing inversion defines a very strong barrier for the convection. And then this process of the near surface heating and the convective intensity build up is associated with the removal of convective inhibition or this very strong negative buoyancy. So when the near surface MSE or cape are maximized, you do see the thing is approaching zero and the maximum, the most negative buoyancy is also approaching zero throughout this time series. So lastly, I just want to show for this part, we also look at the spatial distribution of the actual moist heat and the convection from the EIFR analysis data on the top, and also the potential maximum intensities of the moist heat and the convection defined by the MSE star max or the pre-existing inversion strength. So you can see the inversion strength also capture this spatial distribution of the actual moist heat and the convection on the bottom. If you compare the bottom versus on the top, if you compare the top versus the bottom. But you do see again, the magnitude of this potential maximum intensity for heat and convection are generally greater or slightly greater than the actual maximum, which does satisfy this equation we showed on the top. Okay, so then we have this unified framework, say the inversion constraints the maximum intensity of moist heat and convection across the mid-latitude land regions. Then we can try to understand the projected changes of moist heat and the convection extremes I showed in the earlier slides. And now the question turns to be, can we say expect the inversion changes in the future warmer climate also serves as a very strong constraint on the future co-amplification of the moist heat and convection extremes across the mid-latitude land regions, right? And the answer is yes. And here is what we see about these the projected changes of the inversion based on 4 well-performing models of the CMAP6. So you can see the MSE star max or the inversion is also strongly intensified across the mid-latitude land regions. And quantitatively, we do conclude that the inversion change serves to the first order serves as a very strong predictor or constraint on the intensifications of the moist heat and the potential convection across the mid-latitude land regions. And what's more interesting is that we do see the inversion changes also capture these emerging regional hotspots across the Northeast Asia and the eastern part of North America. And then a natural follow-up question tends to be, what drives the changes of the inversion, especially these regional intensification of inversions across these two emerging hotspot regions? Well, I guess I already show you the answers from my title of these slides, but I just want to elaborate a little bit on about how we came up with this hypothesis. So when we zoom in these two hotspots in North America and East Asia, where the moist heat maximize or the intensification of the moist heat and convection are strongest over this eastern or northeastern part of the continents. But when you look at these two continents, the geographic setup are pretty similar. They both have these high terrains to the west, the Rocky Mountains and the Eastern Highland, the Asian Highland to the west. And these regional hotspots of the moist heat are located downstream of this highland to the west. And these highlands to the west are mostly dominated by relatively dry soil. And then for this dry soil surface over the highland, they do not favor moist convection or moist heat. But instead, we do see the dry heat maximized over this highland surface, especially, for example, over the Rocky Mountain surface, and also these to the west of this highland. What I'm showing you here is the 700 temperature at the height of the terrain surface. The temperature increase in the future warmer climate are strongest above or right above this high terrain surface. So then you can see there are very strong contrast pattern for the moist heat intensification versus the dry heat intensification between these two for these two regions. But then they look different, right? Or not related to each other. But then once we think about this general circulation across the mid-latitude region, it is dominated by the westerly winds flowing from the west to the east, which would serve as the bridge to bring these two patterns together. So you can imagine these westerly winds may advance this amplified warming over the high terrain surface to eastward, which can enhance the inversion downstream above the lowlands of the eastern or northeastern terrains. And this enhanced inversion will further enable the warming or moistening of the near surface heat or the near surface atmosphere, and which also can further intensify the moist heat and the convection across these regions. That might be the reason why these two regions are becoming the emerging hotspots for moist heat and convection in the future warmer climate. So this is a hypothesis we want to test. So basically, we want to see if the amplified highland warming may serve as a mechanism to intensify the moist heat and convection downstream by raising the inversion limits for this across these regions. So to test this hypothesis, I just did a composite analysis using projections in the future warmer climate versus the historical simulations from the CMAP6. So I focused on first a subdomain in the US Midwest, and then to select the extreme moist heat cases across over these regions in between the historical and then compare between the historical and the future warmer climate to see if the dynamical pattern changes are consistent with what we expect to see from the hypothesis. And I think it's pretty consistent because what I'm showing here is the changes for the temperature, which does show a very strong amplified warming over the western high terrain. And then this warming are directly downstream by these westerly winds to amplify the inversion over the Midwest or this eastern part of the United States. And this enhanced inversion will lift the up limit of the moist heat and the convection across this region. And then we see the near surface response to this enhanced inversion. What we see is a very strong moisturing of the near surface atmosphere associated with this advancing of warm and moist air from the tropical region into this local area. So this very strong moisturing and of course some warming together to push this region become this very emerging hotspots for moist heat and convection. I just want to say, we also look at the changes of the vertical profiles of static energy. I just want to say that we see the strongest warming signal occurs nearby this inversion layer, which serves again evidence or fingerprint of the inversion constraint framework we proposed in the previous slides. And again, we look at another subdomain over the hotspots of Northeast Asia, and we see pretty similar pattern changes across these regions. Amplified warming over the upstream highland and advected by these westerly winds to intensify the inversion, and then a very strong surface moisturing to respond to this amplified inversion to push this region become this emerging hotspots for moist heat and convection. And lastly, I just want to show we can also think about to test this hypothesis using some experiments of GCM, right? Because essentially what we showed in the previous slides, we just highlighted this fundamental role of elevated heating by the topography in driving the moist heat and convection extremes downstream over the eastern or northeastern part of the continents. Then we can think about what if we remove the elevated heating over the upstream high terrain surface in the midlatitudes. Then if the hypothesis is correct, we should expect to see substantial reduction of moist heat and convection over the downstream land region, right? So that's what I did using the CSM model. What I did is I conducted two simulations. So one is a control run, a historical control simulation. And then to test this hypothesis, I did an experiment to remove the elevated heating over the high terrain surface in the northern hemisphere. So what I did is to increase the surface albedo increase the surface albedo of high terrain surfaces to increase the albedo to 1. Yes. And then you can imagine this solar radiation in the experiments can be largely reflected back to the space, which will not able to heat the surface of this high terrain surface. Then what you see an immediate response in the experiment is a very strong cooling over the high terrain surface in what you see here in the F. So which is what I want from the experiments. Then we can look at the response of the moist heat and the convection extremes. So again, on the left is the historical simulated moist heat and the convection by the CSM2. And then what do you see the response in the experiments with no elevated heating? So you see a very strong reduction of the moist heat and the convection, especially over the Eastern Asia and the eastern half of the United States. So originally in the historical run, the high values of moist heat and convection extended from the tropical, subtropical to the mid-latitude region. But then in the experiments, without any elevated heating, this high value of moist heat and convection are substantially removed. And these high values are pretty close to the subtropical coastal area. And the underlying physics are pretty consistent with what I showed in the previous slides related to the changes of the inversion. Because in the experiments, we see, as compared to the historical run, the inversion strength is substantially weakened by the removing the elevated heating. So you see the inversion reduction is pretty strong over the eastern part of Asia and also the eastern half of the United States. And again, the reduced inversion will also reduce the convective inhibition across this region, such that the inversion can be easily initiated across these regions. Okay, I think that's basically what I want to show for this talk. I just want to give a conclusion, but want to highlight the inference or this critical role of the inversion from this global scope. So we look at the low-level inversion, but this low-level inversion or thermal inversion actually has been very common across the globe, everywhere. So what I'm showing here is just a very rough results from the EIFI for 1 year, just to give you a sense about this annual frequency of temperature inversions from the EIFI analysis data. So you can see inversion frequency is pretty strong or pretty high for the polar region and also some tropical regions. And for the polar region, this persistent seasonally existing inversion has been commonly studied and has been thought to be related to the surface, can be affected the surface radiative cooling and then affect the Arctic amplification and also the polar atmosphere. And for the tropical region, there are also a lot of study to emphasize this, the critical role of this seasonally persistent inversion in affecting the low cloud feedback, and then can affect the climate sensitivity. But then what my research fills in, I think, is a gap in the mid-latitude land regions. Especially for the mid-latitude land regions, we show the critical role of the inversion affecting the extreme moist heat and the convection events. And the key difference for inversion between the mid-latitude and the other regions is, for the mid-latitude land region, the inversion has more synoptic scale variations instead of this seasonal persistent feature as compared to the polar and the tropical regions. So then I think it will be very important to further study about if like these rules of inversions across different scales for different regions. So yes, I think that's what I want to show. I realize I still have several minutes, maybe. So I have several slides just to quickly finish it. If we can just further discuss about them, just 2 slides. So I just want to mention that some maybe further thoughts I have that I'm interested to discuss in the future work is, we talk about this convective constraints, or this coupling between the convection and the near surface moist heat. I've already highlighted these thermal features of the convection in affecting the heat buildup near the surface. But I would say, when we think about the convective storms affecting the near surface heat, there are a lot of very complicated details associated with especially severe convection in the mid-latitude land regions. For example, the shear influence, which I didn't talk any in the previous slides, but for the severe convective storms, wind shear is also very important to affect the maintenance and also the entrainment efficiency and also the initiation of severe convection over the land region. And all these reasons influence I didn't touch, but I think it will be very important to further think about these different aspects of the storm dynamics in affecting the coupling between the near surface heat and the convection and their evolution in the future warmer climate. And I believe the high resolution model will be very useful to better resolve these storm environments and the coupling with the surface heat events. And I think some very interesting hypotheses we can test. For example, when we further think about the influence of the wind shear, it might be help us to understand how the convection, like the efficiency of the convection in terminating heat waves. And ideally, you may expect if the wind shear is also strong as coupling with together with very strong convective instability, it may enhance the convective cooling efficiency in terminating heat waves. And lastly, I didn't talk about this one. We did look at the bias across these CMAP6 models. The results I showed from the previous slides are based on 4 relatively well-performing models on the left. I did look at some other model. You can see, well, I don't think there is a very perfect model to give very close to observation simulations of the moist heat and the convection, right? Because you do see bias exist just for all these models, especially for the convective available potential energy. For all these models I showed on the right-hand side, these 5 models, the bias is even greater than the true values of the convective available potential energy in across the mid-latitude land regions. So how these bias are produced and how these bias can affect the near surface heat simulation by these models, I think it would be very nice to combine, for example, the inversion constraint framework we proposed in the previous slides to see if we can come up with some ways to constrain the bias of heat and convection across these different models. That's also something we are thinking about to perhaps do some work related to this one in the future. So now this is the real end of my talk, and I'm happy to take any questions.
Thank you, Funing. Lots of clapping, virtual clapping going on that you can see there.
Thank you. Thank you.
So, questions. We have about 10, 15 minutes to ask Funing a few questions. Okay, I have a few hands up. Yi was first. We can't hear you, Yi.
Well, actually, I'm not sure why my hands up, but I do have a
Oh,
question.
okay.
Yeah, I have no idea why the hands up, to be honest. But I do have a 2 questions. Maybe I'll just ask one. Um, So obviously, if I understand correctly about your theory, it kind of assume a clear separation of the timescales, between your boundary layer process and the free troposphere adjustment. I just wonder how often this is actually valid in, the mid-latitude, which is what you're looking at, and the land region where the synoptic scale system can quickly just move through and change the whole atmosphere rapidly.
Yes, I think it's a good question. I didn't exactly, okay, well, I think it's very general to, especially because it's relative with extreme moist heat or extreme convection conditions. Which one you can see from this one, because this is composite time series of the moist heat and convection cases. I forgot how many, but I think it's maybe thousands, maybe for the mid-land regions. But one thing you can see when you look at this composite time series, to look at the adjustment of the free troposphere versus the evolution of the boundary layer, you can see like the 500 MSE star for this composite time series, the evolution or the change is relatively weak as compared to the surface MSE evolutions. So again, just back to your question, I think this relatively constant or fixed free troposphere is quite common to especially the moist heat, severe moist heat and convection evolution cases with relatively short time scales. I think there are also some studies, for example, I believe Ogarde and Emmanuel, and also PJ and Emmanuel, they have several papers to look at this backward trajectory of the air parcel associated with severe convection across, I guess, across many different regions on the globe. They do find that the free troposphere also remains relatively constant, but the free troposphere, but the boundary layer include the near surface MSE and also especially the near surface MSE just evolve quickly within this relatively short time scale. So yeah, back to your question, I think it's pretty general, especially to this relatively severe or extreme moist heat and convection cases of land.
Okay, thank you, Marty.
Hi, Funing. Marty Singh here. Thanks for the talk. I guess I have a few questions, but I'll ask one, and that is, how does this work kind of connect to, say, the work by Duan and Neil and others, where they were focused on the entrainment effect? Because they sort of were looking at the Arabian Peninsula, and it doesn't seem like that's so far south that it would be like completely tropical or completely different to what you're thinking about. So I don't know. How do you think about that, I guess?
Yes, it's really a good question. I would say it's two different mechanisms, completely two different things we need to that's cool. Okay, that's two different mechanisms with this it's not related. It could be related to each other, especially when you think about, okay, first of all, back to your question is, it's two different things. They can both exist when we think about the like the initiation of convection, like to what extent the convection can initiate. The main reasons is for example, we look at all these derivations or all this process, we just based on, let me back to this one maybe. Yeah, we just based on this partial theory or the partial process. So basically, we didn't consider this dilution of the parcel by the entrainment. So this inversion exists, and then we look at how the parcel's buoyancy or the energy compare with this inversion energy, and then we didn't consider any of this entrainment influence. But the entrainment can serve as an additional way to further affect the near surface heat buildup based on this one. I mean, it can serve as an addition because you can imagine if this inversion layer, usually it can be also very dry. So if the entrainment does occur at these layers or areas above, then you can imagine it can further dilute this convecting stability of the air parcel. So you do expect this entrainment or dry air entrainment can further intensify the moist heat and the convection for in addition to what we discussed here. So I think Duan and Nini, their paper still works, and I think it would be very nice to compare these things together to give, as I said, the convection is very complicated, but to give a full picture about how the convection initiation is related to determination of heat waves. And I think one thing I just want to mention is that you do see, for example, these results, some cases, it's not all cases. The reason we say it's a tight limit because you do see it's a reachable limit defined by the inversion. And actually some, but not a lot. But some cases is exceeding this inversion limit. That might be related to some extra influence from the entrainment. But another thing I want to be mentioning that when we start to think about the entrainment influence, especially for the mid-latitude region, we need to be very careful. Duan and Nini, they focus on entrainment on the tropical and subtropical region. I think it's perfect to assume the entrainment is very strong for these regions because the wind shear is pretty weak, right? But for the mid-latitude land region, the wind shear is pretty strong. I think I didn't work on this topic, but I think there are a lot of studies that already showed from the dynamic perspective of the storms. They found that when the strong wind shear exists, it can protect the storm being affected by the entrainment. So you can imagine when the wind shear is strong enough, the entrainment influence might be pretty small to be ignored. So, but for that case, you may still expect this inversion influence exist for these scenarios. So anyway, I think there are different things, but I think it would be very nice to combine them together to give a full picture about these convective constraints on heat waves. But I think, again, be very careful when we translate from the tropical to mid-latitude land regions to think about the influence of inversion of the entrainment. Does that
Thanks
make
very
sense?
Thank you,
Yeah,
Steve.
thank you.
Yeah, Funing, really interesting talk. I like a lot of these ideas. It's becoming clear that that we need to understand the boundary layer better and how it changes if we want to understand heat stress near the ground. I had one question,
Yeah.
which is the one part of your talk I maybe wasn't convinced by was this idea that elevated heating is then advected downstream and that controls the changes in MSE star.
Yes.
From the first figure you showed, it looked like you were showing 700 hectopascal temperature delta, I think, in a warmer climate.
Yeah.
And it looked like it's not that one, it's much earlier one, I think, or maybe around there. And it looked like the temperature change was isolated to the topography, to the Rocky Mountains. But
Mm-hmm.
it seems like for your mechanism to work, it has to sort of spread downstream from there. And it also looked like in your model solutions, the impact on MSE star and Cape and surface MSE was not just isolated to the regions that you were looking at, but it seemed to happen everywhere. So I'm wondering
Yeah.
if you've noticed that and if there might be some other reasons why these particular like Eastern US are being hit worse.
Yes.
Maybe
I think
for example, could the circulation be changing? I mean,
yes,
if you're heating
definitely.
one place and not others, then that's a source of PV, and so then you're just going to change the
Mm-hmm.
winds. And have you thought about
Yes.
that?
Yes, I agree with that. What's the first part? I understand the second part. I can back to that one. But what's the first? You said what do you say? This warming is concentrated over the Rocky Mountains. Then, why this like what do you say about like why this part is sort of not convincing, or what's the concern you say about this part?
Oh, well, it just doesn't seem obvious that the hot heat over the topography will just be advected with the mean winds.
I see.
And if you could find that other figure, it was the first one you showed, uh, showing the delta. No, before that, I think. The keep going earlier. Keep going earlier. Keep going.
No,
Oh,
I think
maybe
that's
I'm remembering wrong. I'm just
something is
remembering I thought
yeah.
it was from a climate change simulation of 700 hectopascal. It was to show us that there was a hotspot. And maybe
Well,
this
it's
is
right
also
there.
showing it.
It's right
This
there
is
on the
showing,
right.
yeah, okay. Well, now it does look like it's spreading out. I guess in the figure I was thinking of, it was, but what is
Yeah.
this showing? This is showing, right, delta T 700. Okay.
Yeah.
All right. So it does sort of look like it's spreading around, but okay.
But
I
I do agree what you mentioned at the second part. I think as you said, like this the inversion constraint is quite general, not only for this for these two regions. Well, I think okay, first of all, yes, back to what you said. I think in general, there are definitely other processes affect the inversion occurrence, right? For example, if you have any large-scale subsidence or these subsidence associated with the anticyclones, this also serves a very efficient way to enhance the inversion within the lower atmosphere. I think, at least for I'm not sure to what extent for these two hotspot regions, to what extent this process may matter, but I believe for especially these Europe regions and also these regions, which is not related to this upstream land surface, these cyclone or anticyclone changes might be more important as compared to these elevated heating processes. Because for this region, you just don't expect any upstream warming to intensify the inversions, but the inversion can still exist associated with this anticyclone evolutions or this change in the future warmer climate to affect the subsidence, right? So I guess, yes, definitely there are other processes to affect this inversion formation and intensification in the future warmer climate. But I think for these two regions, especially for the United States, I think, well, how the inversion forms for this region is sort of, I think I still took some knowledge from the previous literatures because it has been sort of well studied, especially for the central United States, the inversion, what they usually call as elevated mixed layer. They have studied from different ways to show the elevated mixed layer, the source for this strong temperature inversion is from the upstream land surface. And that's sort of, this literature sort of serves as the motivation of my work to say, okay, if that's sort of the source of the inversions across these regions, then if we do see this amplified warming over this high terrain surface, maybe it can affect these inversions downstream. So that's sort of this original motivation of this hypothesis. But yeah, definitely there are other processes to affect the inversion changes and the evolutions. Yeah, I agree.
Okay, so we're running a bit out of time. My main concern, by the way, is that the 700 hectopascal surface does not exist in many of the regions where your hotspots are. The Himalayas do not have a 700 hectopascal.
Yeah.
It's not real.
Yes.
It's 700 was that 3 kilometers. The mountains are much higher than 3 kilometers.
Yeah.
In the Himalayas. So the values you're getting here are model artifacts. They're not there. There's some extrapolation formula from the actual temperature. So I'd be always skeptical about that part, but
I
okay.
agree. Yeah.
I have one last question. Since we're all in the Southern Hemisphere in Australia, you've always showed us Northern Hemisphere pictures. Did you actually look in the Southern Hemisphere and just not show it, or did you not look?
No, I didn't look at that one. It would be really
Okay.
interesting to look at that one. Yes.
Yes, especially for us down here, it would be very interesting.
I know.
So if you have a moment where you can reproduce this for the Southern Hemisphere, we'd be
Yes.
highly appreciated.
I think I'm not quite sure like to what extent like or this process, especially this elevated heating mechanism can be applied to the Australia. But I know for the Southern Hemisphere, definitely South America could be a region. We expect a lot of things we found should be like applied to this region because in terms of this pretty similar geographical setup between North and South America. But yes, I didn't look at them. I think yes, it definitely was to take a look at about this the other regions. Yeah.
Okay, so thank you so much, Funing. We are out of time. Thanks for a really engaging talk and engaging discussion with afterwards. And hopefully we'll stay in touch and you might be able to work with the groups in our center who are looking at moist heat from other perspectives. That would be a lovely outcome. Thanks so much and have a great day, everyone.
Yep. Thank you. Bye.
See ya.
Yeah.